My name is Yuj Kochu, and this is my digital sampling lab, where I did an analysis of noise. So, introduction. The goals of this lab were to become familiar with data acquisition of time-varying signals, to use my own DAC system to sample and analyze signals, to explore issues in sampling, filtering noise, and digitization errors, and to determine the relationship between noise and wave shape. The motivation for this lab was to understand how to observe time-varying signals and to actually be able to learn how to use a DAC system, and to also be able to develop skills that can be used in the future for other data acquisition experiments and other experiments in general. So the background for this lab, noise is an external sound that causes disturbance to a system. It can usually cause a significant amount of error and interferes with the measurements that we're trying to take. So the types of noise analyzed in this lab are white noise, which is on a flat power spectrum, which means that it has the same power at every frequency over a wide range. There's pink noise, which the power spectrum is scaled to the inverse of the frequency. This means that the power of noise at each frequency is inversely proportional to that frequency. And then the final type of noise analyzed is brown noise. Brown noise is typically at a deeper quality, and so it lowers high frequencies by a substantial amount. The first part of this lab, we were given 11 different audio tracks, and I identified which type of waveform was in each audio track. As listed by step 4, I tabulated put in the table the different waveforms associated with the triangle, square, and product of two signs tracks. I identified which tracks those belong to, along with the principal peak frequencies for each one of those, along with additional frequencies that were observed. On the bottom, I have images attached for each type of wave. And so next I have tables showing for different sampling rates that were tested, along with the peak frequencies at each one, and whether or not aliasing was observed in at each one of the sampling rates, and how I determined the cutoff frequency for these sampling rates is that I chose 5,000 hertz because 5,000 hertz is where the frequencies of the peaks start to dissipate and reduce. So the approach for my experiment, the equipment utilized was a LabJack T4 DAC unit, the Georgia Tech Simple DAC software, an audio jack, a microphone, a tone generator, and a noise generator. So for the experiment, I wanted an isolated, closed room so that we could eliminate external surroundings, external noises and factors. And first things first is, before actually collecting the data for the personal experiment, I characterized the equipment, which means that I tested the microphone response at 5 different frequencies with an online tone generator. Shown above is figure 1, where I connected the DAC to the microphone system with the 3 different jumper cables. So for my procedure, the initial settings in the simple DAC, I set the sampling rate to 25,000 samples per second and the record length to 1,000 samples. I decided that this would be a good sampling rate based off of the previous aliasing analysis for the sampling rates listed earlier. The first step is to play 1,000 hertz frequency tone over the simple DAC software. This is going to serve as the control variable, because this frequency does not contain any noise. Next, we'll record the time history plot, and we'll collect data until there is no more frequency and power spectrum data collection. From there, we're going to use the noise generator to play white noise at -5 decibels, and then repeat the steps above involving the noise generator, where we're going to record the time history plots, stop, go back to the noise generator, and switch it to do the same thing, but except for the pink and the brown noises. After the data collection is done, we're going to take all of our TXT files and we're going to convert them to CSV files. From there, I sorted and analyzed my data for each one of those different cases, and I put them in Excel, and from there I generated the graphs for them. So the graph I have created here demonstrates the time history of a 1000 hertz frequency tone with the noiseless tone along with the white, pink, and brown noise interferences. So from here we can see that the white noise, which is represented by the blue color, has a very steep drop along with the pink noise. In the time analysis compared to the brown noise has much less of a drop, and the noiseless has the least amount of drop between all of them. Further expand upon the previous slide, the plot with the white noise we could see had the most impact on the wave shape compared to the brown and the pink noises. The brown noise caused less interruption because the brown noise occurs at lower frequencies, as stated earlier. Through this experiment, I was able to demonstrate the importance of a low-pass filter and how getting the frequencies that you want, filtering out everything else, is really important for data acquisition and for testing. And the noise data analysis from the previous figure can actually be used to reference how to filter external noises and just how to focus on the main signal that you're trying to collect.